So, first of all, let's summarize what we discussed previous time. And previous time we discussed a lot about the indigeneity problem. And I hope that you understand the difference between the endogenous and exogenous variables. But anyway, the main conclusion from the previous lecture, you should remember that indigeneity problem could be a real problem. And because of this, please be very careful when you work with your data and when you construct your models. First of all, let's try to visualize what is indigeneity. So here you can see the dependent variable, set of independent variables, and the error term that includes all unexplained factors and some maybe mistakes in your data, measurement errors, and so on. When there exists some correlation or let's say relationship between the independent variable or let's say independent variables and the error term, in this case, indigeneity appears. And one of the first reasons when this problem appears, you should remember that is admitted variable bias. Because of this, we talk a lot that you need to, first of all, construct your theoretical model, econometric model, in a proper way to include the explained variables that you need to include according to the theory, and also some set of control variables. We discussed a lot about this, so this is one of the reasons, remember about. The second reason could be some misspecification problems, or let's say functional form errors. What does it mean? It means we discussed previous time that, for example, your true population model looks like this. So here's dependent variables GDP per capita. Here's the X is startup activity that we measure using by years of schooling. And also you need to include the square term of this startup activity. But for some reasons, you skip this variable and construct, instead of this model, you construct a model without the quadratic term of startup activity. Again, your result will be the same, the same bet, and your coefficients will be biased and inconsistent. So the result will be the same as in the case of admitted variable bias. And again, the answer how to avoid such kind of problem, please think twice about the model that you use. Next problem is a measurement error. Maybe we don't discuss a lot about this problem, but what does it mean? It means, for example, that let's continue the same case with the GDP per capita, yeah, and startup activity. And let's say that our variable that characterizes startup activity has some measurement error. So some respondents systematically misreported the information about the level of education, about how many years they were educated in school, in university, in college, and so on. In this case, again, you obtain that your parameters will be biased and inconsistent. And the measurement error in the dependent variable also could be a problem, but it could lead only to the larger error variance than when the no error occurs. Okay, so the main conclusion that you should remember, when you have some measurement errors in the dependent variable, and this measurement error doesn't have systematic relationship or correlation with the x variables, okay, you can use this model and obtain the maybe good results if you hold all other assumptions of ordinary least squares method. But when you notice some patterns and when you notice the measurement errors in your independent variable or independent variables, in this case, you will obtain biased and inconsistent coefficients. And this is really very bad. Let's say that another example, not about the GDP, very simple example where your dependent variable is salary. And the salary is very difficult to measure. So let's say that we want to include some variable among the axes that can characterize the intelligence of the respondent. We have an individual level data set. And intelligence is very hard to estimate. How can we measure this? Let's say that we decided to use IQ test, but IQ test cannot properly measure the intelligence of the person. The task is too hard that we can say that if the IQ test is high, that he or she has a high level of intelligence. No, it's not true. So in this case, when your dependent variable is salary, your independent variable is an IQ test, some result, some score, some score of IQ test. So it means that we can obtain some noisy measurement of intelligence. For example, IQ test plus some error, some other characteristics of intelligence that we cannot include and cannot, we don't use some other techniques to measure intelligence and use only IQ test, okay? So in this case, you will obtain here some systematic measurement errors. Next problem that could lead to the indigeneity problem is missing data. We talk during the seminars with my groups, and I think that the other teachers talked with the groups also about the problem of missing values. So the main idea then, when your data are missing completely at random, you can still assume that their data and your model have been obtained by random sampling from the population. And you can work with such kind of data. But if you notice some, for example, you run the description analysis, you describe your data, you use some graphs, you use some tables, and you notice that you have some missing values. And also you see that these missing values have some patterns. So for example, some people, if you conduct a survey, some people are more likely to answer your question. Some group of people, for example, younger people, are more likely to answer your question than the older people. In this case, you cannot say that your data missing at random, because you can see some logic and some patterns again, So let's continue the same example with the GDP per capita. And X here, again, is startup activity. So let's say this startup activity has many missing values. And if the missing values are at random, then there is no correlated with the dependent and independent variables. But here, beta 1 here, will be not biased and inconsistent, so we don't assume any problem. Of course, having missing is not very good situation, but anyway, we can still work with the model. But if the missing values are related to some independent variables, it means that you have self-selection bias or sample selection bias. For example, if we notice in our example with the IQ test and salary, if we notice that some people, let's say that the measure of IQ is missing for 200 of people, yeah? And if the probability that IQ score is missing is higher for people with lower IQ scores, of course, it's not a random situation, yeah? So please remember about this and check your data or work with your data around the descriptive statistics. Check any patterns in the missing values. And one more reason when you can face the endogeneity problem is simultaneous causality. We didn't discuss this problem, but the intuition is very easy. I will explain you and you understand immediately, I think. So let's say that our model looks like this. So we assume that startup activity has some effect, negative or positive, on GDP per capita. We assume that positive, yeah? According to the theory from other countries, for example. But why do you decide that the direction of the relationship only will be like X influence Y in this case? So only startup activity has some effect on GDP per capita. What if the right model will be the absolutely opposite? So now, what do you think if the real model will be like GDP per capita here? Here's the independent variable, has some effect on the startup activity. Generally speaking, both of these models could be right, yeah, because startup activity, of course, can influence GDP per capita, but GDP per capita as well can influence the startup activity. So it's very hard to find the causation relationship here. Where is the reason and where is the effect? And in this case, we talk about the simultaneous causality. And again, we cannot say anything about the direction of this relationship. And in this case, the variable of interest is correlated with the error term. And again, your coefficients, or in this case, coefficient, will be biased and inconsistent. So that was the most of the reasons, yeah, most of the main reasons where you can think, where you can face the endogeneity problem. Please remember about them, because I hope that you work on your research projects, and I think that you work with the models, work with the data, check after this discussion your models, your variables, your missing values, your specification, functional form of your models, okay? Take a look again at your models and your results, if you have obtained already some results. Okay. Now let's start a new topic. All previous discussion was about the models where our dependent variable is a continuous variable. And our discussion of dummy variables has been restricted to dummy independent variables. But you can, it can be easily to imagine that, of course, in real research, we want to work not only with the models where the dependent variable is continuous. Of course, we want to work with the models where the dependent variables, for example, could be a dummy variable or binary variable, yeah? So how can we work with such kind of models? Which methods should we use? How can we interpret such kind of models? And so on. A lot of questions. And today we are going to discuss such examples, such models. They have a broad name as limited dependent variable models. But today we exactly start with the linear probability model and continue with the probit and logit models. In probit and logit models, as well as in the linear probability model, the dependent variable is a dummy or binary dependent variable. What is the difference? Okay, so first let's recall our example from one of the first lectures when we only start our discussion about the ordinal least squares method. The example is very, very easy. We discussed the relationship between the son's height and the father's height. And here you can see the average height of sons, how this value is changed given the father's height. You remember that we can use a scattergram and we can run the regression. So we can draw some line through the observations and you can see these circles. This is an average height of son that is corresponding with the father's height. So this is a linear sample regression line, yeah? It's very easy because our continuous variable or our dependent variable here is continuous. But let's say that instead of continuous variable in this regression, this model, we want to use a dummy or binary dependent variable. This is the same, yeah, dummy or binary, the same. What should we, how can we use, how this scattergram will look like in this case for such kind of model? And generally speaking, we have a lot of examples. We need to put, instead of in the dependent variable, we need to put the dummy or binary variable. For example, the labor force participation. It means that we can code this variable as 1 if the respondent, if the person is takes part in the labor force, and 0, for example, otherwise. Or another example, we want to find what factors determine the use of the debit card. And again, we can code this variable as 1 if the respondent uses the debit card and 0 otherwise. Or let's say that health specialists want to determine whether a person becomes a smoker. if the person is from low-income group of population. Again, the smoking status here could be coded as 1 if the person smokes, and 0 otherwise, and so on. So a lot of different examples. Even if you want to, let's say that you conduct some marketing research and you want to find the preference of customers, you want to, for example, you have a task. You need to find and explore the factors that influence if the person will choose to buy a Coca-Cola instead of Pepsi, or to buy the iPhone instead of Samsung, Apple instead of Samsung, yeah? So a lot of different examples. In all of these examples, dependent variable is a binary variable. So how can we deal with such kind of models? First of all, we need to find the difference. In a model where your dependent variable is quantitative, our objective, you remember, yeah, is to estimate the expected or mean or average. Yeah, when we interpret such kind of model, we always add the phrase on average. If we increase some factor by 1 unit, our dependent variable changes by some value, holding all other factors fixed on average. Okay, this is good. But when you work with the qualitative dependent variable, in this case, your objective is to find the probability, and this is the main difference. Now you will work with the probability of something happening. In general, we name this success or failure. Yeah, if something happening, it means that your dependent variable equals 1, will be coded as 1, and takes the value 1, and this will be in general like success. For example, owning a house. Yeah, here so you can read this example. So if the person owns the house, your dependent variable equals 1, and you want to find the factors, the effect of different factors such as age, such as income, such as, let's say, region, such as the number of persons in the household, and so on. How these factors change the probability that the person will have the house, the home, maybe the apartment, not exactly the house. So this is the main difference, of course, the first one. And because of this, qualitative response regression models are probability models. Okay, but also we have relevant questions. Okay, this is the difference. Now we talk about the probability, but the next question is, how do we estimate qualitative response regression models? Could we still use the ordinal least squares procedures? Because we talk about these procedures a lot. We learn the assumptions, or we learn how to interpret the results from these models. We've just finalized some common errors. We talk a lot, and during the seminars you have a lot of classes on this topic. So can we simply use the same approach? And the next question, are the special inference problems? And also an interesting question, if a regressant is qualitative, how can we measure the goodness of fit of such models? For example, could we still use the R² or adjusted R² or F statistic, yeah, of some, to say something about the goodness of fit of such models? So now let's discuss all these questions step by step. But first of all, let's say that we keep ordinal least squares approach and continue. We now work with the model where our dependent variable is binary variable, not a continuous, and our independent variable, let's say, will be a continuous variable. Even in this case, we still be able to fit the line. You can see now how the line looks like. Yeah, this is our regression line. This is our observed values. You can see here exactly two clusters of observed values. One of the clusters at the bottom left corner and the second one at the top right corner. So it means 0 and 1. You can see here exactly the values corresponding. So because this is dummy binary variable, yeah, it's obvious. But is it still possible to estimate the beta parameters using such scattergram, using such line? The answer that it's indeed still possible to run the regression with the ordinal least squares method. But you can notice even from this graph some potential problems after you run such kind of regression. You can see here the first problem, that the line should, if you remember our point that we work with the probability now, we can assume that the line should lies only in this range between 0 and 1, yeah, because we talk about the probability could not be higher than 1 and could not be smaller than 0. It will be very strange and it will be wrong. But the line, as in this example, of course, could lie higher than 1 in that area and could lie in the area that specify values less than 0. This is the problem, the first problem. But let's continue our discussion. So let's say that we keep ordinal least squares method and we continue to work with our model where our dependent variable is binary. So we can use the general notation. This notation looks very similar as usual. We work with the regression with the ordinal least squares method, of course. And just remember that y is binary now. And again, we should assume that the zero conditional mean assumption, yeah. And you remember that we can rewrite this notation through the expected value, conditional expected value. But now, instead of dependent variable here, you use the probability of success that something is happening. Success here again means it depends on the context of your research. For example, if you coded your variable 1 as 1 where the respondent has a work, it means success, okay? It doesn't mean that something is good or something is bad. It only depends as you coded your variable. And here, the probability of success is a linear function of some x's, linear function. So you have the same slope, it means, yeah. And also you can see that betas here measure the change in the probability of something is happening when x changes by 1 unit, for example, increases by 1 unit, holding all other factors fixed. So remember about the difference in the interpretation. Now you interpret the change in the probability, and this is very important too. Don't be confused. Don't forget about this. Sorry. So the general question was, could we still use ordinal least squares method? And the answer is yes. It's still possible to use ordinal least squares to estimate the linear probability model. But now you need to interpret your results at the conditional probability. And if you remember that the dependent variable measures the probability, you can also assume that dependent variable, of course, follows Bernoulli probability distribution. And in this case, the probability must lie between 0 and 1. And this is the restriction of this model, because this restriction is very, very strong. Okay, what problem could we assume if we continue to work with the ordinal least squares method when our dependent variable is binary? The first problem, that the disturbance term doesn't follow the normal distribution. We just discussed that now it follows the Bernoulli distribution. And maybe ordinal least squares method doesn't require the disturbance to be normally distributed itself. Yeah, we need this assumption for the statistical inference for small samples, especially. Yeah, because if we work with the large samples, we assume that in large samples, the error terms follows the normal distribution, approximately normal distribution. And now, unfortunately, it doesn't follow anyway. The normal distribution follows the Bernoulli. But even in this case, non-fulfillment of this assumption of the normality distribution assumption of the error term may not be so critical, because we still obtain unbiased and consistent estimators if all other assumptions holds. This is not the main problem. The second problem that could arise is that we cannot hold homoscedastic assumption. Because again, the variance of our error term depends on the values of x, and it's not homoscedastic. The third point here we've just discussed, but this is one of the main problem in the linear probability model, that unfortunately ordinal least squares method doesn't take into account the restriction that now the probability and your dependent variable should lie within the interval from 0 to 1, because ordinal least squares assumption doesn't understand that you work with the binary variable with some probability. It's too hard for such method to understand this. This method works with the continuous dependent variables. So, and the last point, the last argument that it's not better to use the linear probability model, that R squared and adjusted R squared in such kind of models cannot properly say something about the how good or how bad your model in general. Because when the predicted values of your dependent variable are not between 0 and 1, R squared must be lower than 1. Much more lower, I should say. And this will be a problem, yeah? So again, please take a look at the graph with the more details. So you can see here again some observed values. This is a general example, yeah? Here's your estimated regression line. And you can see how dependent variable moves here, moves linearly from one extreme to other extreme. And in some cases, when you have very high or very low, very small, let's say, values of independent variable, in this case, you can obtain the values of your dependent variable outside the meaningful range of 0 and 1. 1 like here and 0 like in this case. Okay, so if you want to run the linear probability model, instead you just can run the command regress. After this, specify your binary dependent variable, and all the other steps will be absolutely the same as you do when you work with the ordinal least squares estimated with the continuous dependent variables, okay? What can you see here? You can note that we obtain in this example, as in most of the cases, very, very small value of R squared indicator. And anyway, you see here some coefficients, you see here some statistic, that inference statistic that associated with the coefficients. So you can say something about the statistical significance of your results. You can say something about the direction, and even you can interpret the coefficient themselves. So how can you do this? You should remember that the main difference, again, now when you interpret the coefficient, you should interpret the effect on your dependent variable in terms of probability. Please remember about this, because the linear probability model represents the change in the probability that your dependent variable, in our case, this is self-employment status, equals 1. So if the respondent is self-employed instead of paid worker, yeah, and this change in probability caused by 1 unit increase in the independent variable, if we talk about the continuous independent variables. If we talk about the, let's say, dummy or categorical independent variables, you should remember that you compare the groups with the base group. Okay, so for example, how can we understand this coefficient? Minus 0. No, let's say that this one, this coefficient is higher than the previous one. So 0.02 positive effect. So how can we say? It means that if the person is married, yeah, has a wife or husband, depends on the gender, yeah, and the preference of the person. In this case, the probability that the person will be self-employed is higher by this value, by 0.02, holding all other factors fixed. Okay? I think that this is rather easy because we talked about the ordinary squares method, so the interpretation is almost the same, but please remember that now you should interpret in terms of probability. But here you can notice the one more problem, yeah, not only here, but also from this graph, yeah, that the probability cannot be linearly related to the independent variables in all cases, yeah. And linear here, the line here, and this linear relationship here means that the effect of the independent variables is linear, is the same, let's say, is constant on the probability. And sometimes it's very hard to imagine such situations where the effect will be constant on the probability. For example, let's say that we want to discuss how the woman decide to go to the work or to stay at home with the children, for example, or just stay at home and don't have any job. So how can we work with, how can we interpret such kind of results? We predict that the effect of going to work when the number of children changes from 0 to 1, reduces, for example, the probability by some value. Okay, but it seems more realistic to assume that the first small children, let's say some baby, yeah, would reduce the probability by a large amount, but subsequent children, for example, if the woman has, if the family has more than 4 or more than 3 children, so the probability of working if the woman will be work in such kind of family will be not the same if we compare with the family that has only 1 children, yeah. So it's very hard to imagine that the effect on the probability will be constant. It's not right. So this is the second problem. The first, we discussed that the first main problem we discussed that in most cases you can obtain some values, the predicted values of your dependent variable that higher than 1 or less than 0. And the second main problem, if we use linear probability model, that you have a linear effect, the constant effect of your independent variables on the probability. And in most situations, this is also not true. This is not right. Okay, so let's summarize the sorry. Let's talk now about the limited dependent variable models. So the fundamental problem with the linear probability model it's not logically a very attractive model because we've just discussed at least 2 reasons why it's not a good model. Because the unmeaningful predicted values of probability, yeah, of success of some event. And the second, that probability increases linearly with x, or in other words, the marginal or incremental effects of the independent variable remains constant. This is wrong. Because of this, when you work with the binary dependent variable, it's better to work with the specific models. They are broadly defined as the limited dependent variable. But limited dependent variable models includes not only when you have a model with the binary dependent variable, it also includes when you have a model with, for example, categorical variables, yeah, or any models when the dependent variable has a some limited range of possible values. Okay, not a continuous range. So the limitations of the linear probability model can be overcome by using more sophisticated, or let's say more relevant instruments such as binary response models, or to be more precise, we can use logit or probit models. This is the specific names of the models, and logit and probit models are included in the limited dependent variable models. As an examples of such models. Okay, so the intuition behind such kind of models is very easy. The econometric problem is to estimate the conditional probability that dependent variable will be equal 1, conditional on some independent variables. So we need a model, we need some probabilistic model that has these 2 features, very important features. The first one, as x increases, the probability of the success increases, but never steps outside the 0-1 interval. And the second one, that the relationship between the probability and x is not linear. So it means that one which approaches 0 at slower and slower rate as x gets small, and approaches 1 at a slower and slower rates as x gets very large. So let's try to visualize this model. How should it look like? You can see again some observed values. Let's say that this is market cap, and the dependent variable is probability of paying a dividend. And we have 2 clusters again of observations. The first one means 1, that the dividend will be paid for the people, and 0 otherwise. Yeah. So the elegant decision in this case, that we just change the line, instead of line, we should draw here some curve. And if you take a look at this curve, you can notice that this is really good solution. And it looks very similar as a cumulative density function. So now the model this model that the probability lies between the 0 and 1, and the relationship is non-linear between the probability and between the independent variables. This is a kind of S-shaped curve, yeah? And it looks like the cumulative distribution function. The practical question is, which cumulative density function? All CDFs, all cumulative density functions, are S-shaped. For each random variable, there exists a unique CDF. So which one should we choose? And to answer this question, we can use two functions. The first one, let's again take a look at this slide. So here's some G here. Instead of G, instead of this dot, we need to specify some specific function. So what should we plug in here in the brackets instead of this dot? And if you plug in here the standard normal distribution function, it means that you use probit model. You should remember, yeah, that the standard normal density function looks like this, but instead of this thing, you should put here this expression. This is the expression of the standard normal distribution. And now your regression model looks like this, where the phi is the cumulative distribution function for the standard normal distribution. Maybe it looks a little bit complicated for the first time, but the idea really is very, very easy. You need to find just some function of the cumulative distribution. And when you work with the probit model, it means that you use standard normal distribution function that looks like this. So the estimating model emergence from the normal CDF is known as the probit model. And when you want to estimate such kind of model, you cannot use ordinal least squares method. Instead of this, you need to use the maximum likelihood method. We discussed next time what does it mean. I don't want to overload you with a lot of information about new models, about new approaches. So let's delay our discussion about what is maximum likelihood for the next time, okay? Just for now, just remember what is probit model and which function the probit model is used. The second thing, the second approach that you can use here, instead of standard normal function, you can put here the logistic distribution function. So you have two choices. The first one, you can determine the CDF with the normal distribution function, and the second one with the logistic distribution function. If you use the logistic distribution function, this leads to logistic regression or just logit or logit model. Also, I hope that you remember how it looks, how the distribution function of logistic function looks like. Here's the answer, yeah. And instead of Z here, you need to put the model of your regression. And the final expression looks like this. So here's your dependent variable. This is some expected value that the dependent variable equals 1, or here's the probability, yeah. And here's the logistic distribution function with the parameters from your regression. And again, if you want to estimate logit as well as probit, again, you need to use maximum likelihood method instead of ordinal least squares method. Okay. So maybe it will be easier to explain the basic ideas underlying the logit model if we present this as a ratio. So if we present the logit model as a ratio, let's say our example about if the respondent has their own home, it means 1, yeah, the variable takes the value 1 in this case. And otherwise, if the respondent doesn't have their own house or apartment, in this case, the dependent variable takes the value 0. So this is the expression when the probability equals 1. This is the expression when the probability equals 0. If you want to find the ratio, yeah, of probability that dependent variable equals 1 and the ratio that the respondent own a house to the probability that it will not own a house, you need to construct some fraction, yeah, you need to construct this ratio and combine these two expressions. When you combine these two expressions, the denominator cancels out and you just obtain this easy expression, yeah. But it will be much easier to interpret this equation if you take a logarithm of both sides, because now after you take the logarithm, here will be the logarithm of odds ratio, yeah. And in the right side, you just see the linear relationship of betas and the variable, independent variable. Okay. Again, do you understand what is odds ratio? Guys? Anybody here?
So it is range probabilities of dependent variable is successful or not successful.
Yeah, it's just a ratio of two probabilities. So when we will interpret logit models, of course, we will interpret the logit as well as probit models in terms of probability. But sometimes in some researches, in some studies, you can use odds ratio instead of probability, because odds ratio also is a good measure of some effect of independent variables on your dependent variable. Okay, so if you want to run the probit model in Stata, you just need to write the command in your code, the command probit, and the last part of your expression will be the same, absolutely the same as in the ordinal least squares method. First, you should put the dependent variable, your binary variable, and then your independent and control variables. And you will obtain very similar to the ordinal least squares after the regress common table. Again, you can see here some coefficient, some statistics that associated with this coefficient, again, some general characteristics of your model, but instead of r squared, here you can see pseudo r squared. In general, they have the same sense, the same function to help you to estimate, to say something about the general goodness of fit of your model, but we will interpret what does it mean next time, okay? But if you run the logit model, again, just type logit, and again, you will obtain the very similar table as the previous one after the probit. Again, the same statistics and some coefficient. But now I can say this word, but the problem is you can take a look at this table as well as this table, yeah, after the probit and logit models. But you cannot interpret the coefficients after the logit or after the probit model directly from this table. What can you do? What can you interpret from this table? Yeah, you can interpret from this table only the statistical significance. Yeah, again, you can use some p-value, some confidence intervals here. Even that statistic have the same function of the t-statistic, yeah, the same meaning here. And also you can say something about the sign, or let's say the direction of the relationship between the independent variables and your dependent variable. And that's all. Let's combine all three models in the one table and discuss with the more details what does it mean. Okay, so as expected, the second and the third column here is the results of coefficient and associated standard errors after the linear probability model. The first example that we discussed, the model with a lot of limitations, yeah. The third and the fourth columns here is the results, again, coefficient and the standard errors from the probit, and the last two columns from the logit models. So what can you notice? If you compare all the coefficients here from three models, you can see that generally speaking, you obtain the same results in terms of significance and in terms of the direction of the signs, yeah? And in most cases, if you compare LPEM, probit, and logit, you will see that the results after these models are very similar. Again, similar, I mean in terms of significance and in terms of the signs. Of course, they are very different if you compare the value of coefficients itself, yeah? So again, if you want to interpret the linear probability model, you should remember that the slope, this is the slope, yeah? Or this is the slope. So the slope coefficient measures directly the change in the probability of an event occurring as the result of a 1 unit increase in your continuous dependent variable. Okay? In logit model, the coefficient measures some change in the, and now please attention, some change in your dependent variable, whereas your dependent variable, even not directly the probability, your dependent variable here, if you take a look at the slide, this slide, your dependent variable here is the logarithm of odds ratio. And really, it's very hard to understand what does it mean. So, okay, odds ratio, we can understand what does it mean, but logarithm of odds ratio is too complicated to understand. For example, if this value very small or not so small, this is logarithm of odds ratio. So because of this, you cannot directly interpret this coefficient, the size of this coefficient, yeah, the value of this coefficient. Again, yeah, so the 1 unit increase in the independent variable leads to some change in the logarithm of odds ratio. If we discuss the logic model, if we discuss the interpretation of coefficients in the probit model, it's much more complicated even in the logic model. So in probit model is the rate of change in the probability of somewhat very complicated, because if you take a look, what does it mean here, yeah? And if you try to plug in here these expressions, this expression and this expression here, yeah, you can see that the dependent variable here is something very, very complicated that you cannot interpret directly from the coefficients, of course. Because of this, after the probit and logic models, you cannot interpret the coefficient itself. Yeah. The value of the coefficients, again, I mean. What can you do? Instead of this, you need to use the partial derivatives. We will take a look how can we do this in the lecture. And also you will have enough practice how to do this in the seminars. Okay, you will interpret a lot, you will have a lot of practice in interpretation in such kind of models. Okay, now let's stop here. First of all, do you have any questions? And second, I have my own questions to you.
There was a question in the chat during the lecture. I don't know, did you see it?
No, unfortunately no, because I demonstrate my screen. Excuse me, I was wondering why we always don't obtain R squared adjusted when performing robust regression. Why we always don't? Because the Stata software is calculating in such manner that you cannot obtain after the robust standard errors these indicator. But when you use a store and a stop command, yeah, and in most cases now you need to use only a store and a stop command because you need to combine all the results from different models in one table. You can add very easily R squared or adjusted R squared or IEC, BEAC, and other indicators, all that you want. So it's not a problem, okay? Please use a store and a stop command, okay? Now